All right, thanks everybody for joining us today for, I think this is the fourth week in the HPC CI training series this year. I'm Marty Kandes. I work in the HPC user services group. I've sort of been, I think, attended most of the weeks just to sort of help out with the chat and stuff. So we may have spoken before, but this is my first presentation for the series. And this talk is on Singularity. It's a container platform for scientific and high performance computing that you'll find on most HPC systems these days. And so this talk I've given for a few years now. It's kind of evolved and sort of how in depth it went into. This is more of a introductory level where we're really just going to talk about what Singularity is, why it's useful, and just give you the basics for how you can get started using it and why you might want to use it in either in your research, or you may just have to use it at some point for some application that you're using. Your colleague might have developed some code that you need to run, and the easiest way to do it is in a container on some of these systems like Expanse. So that's kind of the idea of today's talk. We have way more time than I usually have to give this talk. I didn't really have time to update it for a full 2 hours. So we can definitely, I'll try to do some hands-on, examples and things, because some of the screenshots you'll see in the talk aren't quite updated to Expanse yet. It's sort of still screenshots from our old system comments. Okay. Okay, so yeah, that's the agenda for today. I kind of already said that. So we're going to review sort of what is a container for people who don't know what a container is, what Singularity is, and why it's useful in the HPC space, and sort of what it can do for you for your graduate student, professor, either doing research or teaching computing, but how these things are useful for the space. And the first sort of analogy you usually see if you ever have watched a introduction to containers talk in computing, they give this analogy of they're like a shipping container, right? And so this is, I've grown to enjoy the analogy a bit better over the years as I've gotten familiar with containers. And the reason they make this comparison to a shipping container is you have to think about what shipping was like before the modern shipping container. And this was before containerization in sort of the global trade system we have now, right? Everything that was shipped around the world was really packaged in its own unique way, right? This sort of way of, depending on what you were, shipping, maybe it came in a barrel, maybe it came in a box, maybe it came in, all sorts of different types of containers, right? And sort of individually was always packaged by hand, right? And so this was sort of very inefficient, not only sort of, having all these different types of, packages and containers for the different goods that were being shipped around. So it was hard to come up with a system to load and unload them from the ships. So it took a lot more time for when ships came to port to, unload the cargo and reload a new shipment to take back to, maybe the last place they came, right? You can also imagine this was a little bit insecure, right? So that, these were sort of all handled by hands as people moved the stuff off the ships or onto the ships. You had a lot more access to, oh, what is this product here in this box? Let me check real quick. Maybe I want to take some home if you're not getting paid well or something like that on the docks, right? And this also created the problem where, this extra expense of this sort of unique packaging and movement of goods, it was really hard to make it cheap, right? So you really only ship things that were, high luxury or specialty goods long distances, right? Most cargo was only shipped locally, like in sort of a region. There wasn't a huge global trade industry like we had today, right? So after sort of the invention of the modern sort of shipping containers, right, you had this sort of standard box that people could just, anybody who had goods that they wanted to get from one place to another, they would just package it into this standard size box. There's actually, I think, 2 standard sizes. And you would load it at the place of basically the production of the goods, right? You knew exactly how much stuff you could put into these containers. There was a known size, a weight tolerances, and all this. So this made it much more efficient to load these things on, anything from trucks to rails to ships, and it was all, in this very standardized process. Again, it also solved the problem of like the security, right? So all the dock workers and the shippers need to touch is, moving the container onto the flatbed of the truck or onto the train or onto the ship. No one actually has to go inside and see what's actually in there, right? It just moves from one place to another, completely locked from point A to point B until it gets to the customer, the end customer, right? So this really changed the way sort of global shipping works, and sort of obviously I think everybody's not more familiar with supply chain issues the last year and a half or whatnot, but this is kind of a good analogy for what we're talking about with computing and shipping containers. So how is computing like shipping, right? And the thing is, how computers sort of physically look and sort of how we program them and do our work on them has changed over time, just like in before containerization in shipping and after containerization shipping. Like if you go back into the sort of the evolution of computer hardware, right? These are a few examples. You physically had to program the computer by hand back in the day. Sort of pushing wires here and there and flipping switches and dial, turning knobs and stuff like that, right? Or at one point, well, you got a little bit more fancy. You have still a room-sized computer, but now you have like things like magnetic tape, but you still are using things like punch cards, actual physical pieces of paper that you slide into the machine to program the computer. And then you had floppy disks and CDs, and today you can even just from your laptop, from your own personal computer, you can order a computer off the internet in the cloud on, say, Amazon, and work there, right? And the interesting thing is, if you think about this, right, these different physical ways that we interact with computing resources, and at the end of the day, we want to run our software on them, right? We want to run our research code or whatnot. And if you think about like, in at least probably 3 of these pictures, right, Fortran was running on all of them, could run on all of them, right? So I'm a Fortran programmer by training from grad school. So I mean, the Fortran was running on the mainframe here at the bottom left, to the PC in the 90s, to can run in the cloud today, right? And the thing is, right, that code is the same, basically, essentially, right? The source code, if it's written, at least in older variants of Fortran. But how you get that code into each system and run it, is different, right? Even though the source code may look the same, how you get the code physically onto the system and run it, compile it and run it, is very different, right? And so that's what we're talking about here, even today. Even though like most HPC systems you're working on in your research, you're going to experience like each system has its own unique software environment, right? Now it's much easier to get your code onto the system. You just download it from GitHub, and that's the same. But once you get the software to the system, each system is a little unique, and how you compile it and the different compilers that are available, they're all different, right? And the different, some systems may have even different operating systems, and so it's a little bit of a challenge when you first get started. Just bring it. It's easy to get your code there, but then you have to like compile it and run it and get it going, right? And it's a little bit unique on each system, right? So this is just a comparison of like one of my codes from my GitHub, right? So I download it from on Comet, was our old system before Expanse, and this other system, Stampede 2, which is in the Exceed network. And I just clone it and just run my make file. And you can see that just the same code that I know very well. I run the make file. I know these systems both pretty well. You're going to get just different output, just even on the compilation, right? So you can see there's differences of different, warnings and things depending on the compiler you're using on one system or other. So it's a unique process of getting things going when you compile your code and run it onto each system, right? And so that's what a software containerization is. The problem it's basically trying to solve. It's really trying to solve this problem of being able to take your code and put it in, package it in a certain way where you can run it almost identically anywhere you take it, right? And so this notion of a software container, right? It's a little difficult to explain if you have to dig into the details of sort of how these things work, but it's really a set of technologies that help to solve this problem of making your your code reliably, reproducible and runnable anywhere you take it, right? When moved from one computing environment to another. And so it's the set of technologies that help you do this, but the how it manifests itself when you're using, that you'll see when you're using containers, is there's really two ways to think about containers. There's something called a container image, right? So when people say, when they're talking about a container, they might be talking about the container image. So the container image is really a file or a collection of files, saved on, storage on disk that's stores everything you need to run your application, code, runtime, system tools, libraries, and even like sort of an operating system flavor of your choice, right? So it really is, the container image is this packaged file, or depending on which kind of container engine you use, collection of files it can be, that has everything you need to run your code, right? It's that thing that you will take from one system to another to run your code. But when you get your container running, people might also refer to the container as the running container, so the container process, right? So anytime you run a container, it basically runs as a standard Linux process. So if you use top to look at when your code's running on a system and things like that, you'll see exactly the same thing you would see if you ran your code not in a container, but the process that's running is running with that environment that was stored in the container image, right? So the process is really sort of encapsulated inside that environment that you created in the image itself, right? So yeah, I'm just here showing in some of these screenshots, you have I'm running some Python code here, and it's really just it just looks like a standard Python process that's running. Oh, this is a GPU specific example. So you can see my GPU code is running on this third GPU here. So it really just looks like, if you've used these tools to just look at your processes before, it really just looks like a Linux process. And if you've seen the movie The Matrix, this is kind of my analogy for what a container is, I guess, if I haven't explained it well enough yet. So if you've seen the movie, you'll get the analogy. But the container compared to the supercomputer is really like this thing called the construct to the matrix in the movie, right? Where they basically have this program or this environment where they can create anything they need to take into this virtual world, the matrix, right? So you can think about the container the same way. It's this loading program or environment where you can put anything you want in there and take it to any supercomputer you need to, right? And in general, it should run seamlessly across all of them, right? That's the whole idea. So let me stop. There's a few things in the chat. I'll maybe see if there's any questions before I move on.
It's on me, Marty.
Oh, okay. Never mind.
Yeah, you're fine.
Okay, cool. So that's what a container is, and sort of why it's, what the big idea, the overarching big idea is of why people are interested in these things. Now, if you've worked with in computing for a while, you might have used virtual machines, like say on Amazon EC2 or some sort of OpenStack cluster, right? So one of the questions, if you've never worked with containers, but you might be familiar with virtual machines, is how they're different, right? Because virtual machines were invented to sort of solve a similar problem where you have applications that you want to run, but you want to control the environment, the software environment that they're running in really well, but that you want to also abstract it away from sort of the underlying hardware that it's running on. And so The main difference between containers is they're much more lightweight than virtual machines. And this essentially, when you have a virtual machine, right, it's really emulating a lot of the hardware layers in the computer in software, right? That's why they kind of run slower, right, depending on what you're doing, right? So in general, there's this extra hardware abstraction layer that really slows things down, where containers get rid of that. And essentially what they do is they directly talk to, say, the underlying Linux kernel. So it's really close to of the host system, right? So you're really close to the underlying host system. You don't have all this hardware abstraction going on. So you basically, the container gives you a much more performant application when you're running in a container versus a virtual machine. So that's like the big first, advantage is this near native application performance. Again, the whole idea of containerization is to you bring your own software environment, your own code wherever you want, and run it. So you have that sort of freedom of movement between systems without the hassle of having to set up your application every time you go to a different system or have access to different resources. The nice thing about containers as well is, especially in the scientific computing aspect, is you create this container image, this pre-packaged set of software applications and environment. It gives you this sort of scientific reproducibility, right? So there, if you are running some code for simulating some science, your oceanography, physics, whatever it is, you're doing some specific set of simulations, right? You can have this packaged software environment, run all your simulations through that packaged environment. And then when you publish the paper from those simulations, you can literally publish that container and the code as well. And other people should be able to verify the results from your paper, right? So, reproduce is a big thing these days in science in general. So this is kind of, if you're doing simulation work or data analysis, this is one way to increase your, scientific reproducibility. And then again, most of these container engines that you'll see and hear about, they're built on just basic standard Linux technologies. So it's basically available on any Linux distribution you might be using. And you get this portability aspect of the container. Again, build once, run almost anywhere. So the almost is the parts we'll talk about later, but we'll get there. Well, I think there's maybe the next slide. There are some limitations, right? So there are a few things that limit this portability, right? So there's always going to be a difference between a container built to run, say, on an x86 architecture versus, say, an ARM architecture, right? So you will have to rebuild containers depending on if you're running on special hardware sometimes, or not special hardware, but different computational architectures, right? Different computer architectures. You have to address that when you run on different types of systems, which is going to become more common, I think, over time. I mean, I think ARM is coming up in the world for supercomputing, so you might run on ARM machines, in the not too distant future as well. Portability, right? So there are some portability issues, right? So because the containers are so close to the underlying hardware and relies on sort of the underlying Linux kernel and some of the libraries, you do have some dependence on that and a requirement to meet certain standards. So usually this comes up in a couple different ways. So the one I actually don't have here is in terms of operating system requirements. So usually when you're building a container, right, you choose what version of an operating system you want to run, right, inside the container. For example, on Expanse, right, if you log on to Expanse and check what type of Linux we're running, it's like CentOS, I think 8.3, right? That's just the native underlying operating system. But most of our containers that we use are based on Ubuntu containers, right? So mostly 18.04 right now. I'm hoping to move to 2004 in the not too distant future. But as you move versions, say in that Ubuntu line of R containers, right? The newer operating system, say the Ubuntu, they're going to have probably a 2204 come out this year, usually relies on, some minimum Linux kernel version, right? And so if our kernel version, though, on Expanse on the host system in that CentOS environment is too old to run the kernel requirements of that newer operating system in the container, that's one place you can run into some compatibility issues. Usually that's, takes years for that sort of gap to widen. But you also run into these issues when you're using specialized hardware like the InfiniBand, the high-speed InfiniBand network on Expanse, or say NVIDIA GPUs. There's also drivers and things that there's always version requirements, and if the versions that you install inside your container aren't compatible with the ones on the underlying host system, you can run into some issues, right? And the last point here is file system isolation. And so what this, I don't know if this is really a limitation, this is just how things work. It's just that when you use a container, right, you by default basically don't have access to the file system on the host, right? So so if you want to see files that are outside the container, you kind of have to explicitly say, hey, container, I want you to be able to see this file system so I can get these files outside of the container, right? This is not a big problem, but it's just something to be aware of, that, the container really does have its own sort of file system on the inside. And so if you want to poke out and use files on the outside, there's a way to do that. It's just, this is part of the process of using containers. Now, if you've heard about containers before, you've probably just heard of Docker, right? So this is kind of the most common container platform in use today. Provides basically, tools to create, maintain, distribute, and run container images. But it was really designed for a different type of space in computing, right? It was really designed for these sort of network-centric service architectures, web servers, databases, anything to do with sort of web development is kind of where it came out of, right? So that's what the configuration and sort of how Docker was designed to run came from that sort of mindset, right? But it's really easy to install. It's well documented. You can install it on pretty much any operating system these days. A lot of big user community, container ecosystem. You can grab a container for probably anything that you might never have to make your own container if you use a Docker container. I don't know, but it's if you're interested in playing around with a different container engine besides Singularity, which we'll talk about today, obviously, this is something that you might be interested in checking out.
Marty?
Yes.
I'm going to interrupt, and we have 2 questions in the chat.
Okay.
Do you want me to read it to you, or just going to look at it?
I think I can see it here.
Okay.
Okay, I think the first one is from Anmol. Is it generally possible to use a container package using Ubuntu 12 on Ubuntu 20, assuming same hardware architecture? Yes, I think I haven't done a lot of I haven't done a lot of work on sort of using really old. If your question is that if I run this really old version of Ubuntu in my container, will it work running when the host system is running a new version? In theory, it can, right? That's sort of one of the points. We don't do that often, but sometimes people will come with code where it's so old that it hasn't really caught up to sort of using newer libraries and things, and we find weird compatibility issues, and we have to put them on an older operating system in the container than we're running on the underlying host system, right? So how far back you can go, though, is it's probably an open question depending on what you're trying to do, right? So, but yeah, that's definitely one of the applications where you have code that used to run in a very old operating system, which no one runs anymore. You can try to run it in a container. So the next one is from Maria. Does the container call the underlying software and libraries it uses, excuse me, such as Python, MPI, libtraffic, etc., or does it contain all of the actual files and libraries? So this is a good question, and you can do both, right? In general, you don't want to do the first option, right? So you can, if you had to, use software outside the container, sort of what we would call bind mount the software into the container. So essentially, remember this process I said of if you want to use something outside the container on the file system outside the container, you need to sort of poke a hole outside the container and bring it in essentially to be used by the container. And so you can do that with software as well. It's tricky, I would say, because the nice thing about putting everything you can in the container is that you have this unified software environment, right? When you start trying to use, say, which one of the best examples is people do this. I'm not a fan of it, but where they want to use, say, Intel MPI. So they want to use the Intel MPI that's available on Expanse, but they want to use it through a container. And we don't distribute, there's software licensing rules, right? We can't really distribute our version of Intel MPI in a container because we can't sort of just hand it out for anybody to use. So in certain cases we have done this where you can sort of put everything that the user needs into the container and then bring in the MPI from the outside and compile things in the container, and then it'll run. But then the problem then is with that sort of a model, even though you can do it, then that container is tied to that system and that MPI. So it's kind of defeats the purpose of doing the containerization unless there was some other, important need to have the container available. So yeah, it's, usually you would want to put everything that you need to run your code in the container and sort of, try not to use any software outside the container. So that's kind of the answer there, but very good question. Yeah, so yeah, I don't know if I have that slide. So I used to call those, I think, exoskeleton kind of containers where you have sort of build the container around some software on the outside, but I don't think I have that slide in here. Okay, so Docker, yeah. The problem with Docker is it wasn't, again, designed to really be run on HPC kind of systems, right? It was really designed for this sort of, web forward model, right? So, and one of the fundamental problems with Docker is the security model it has. It really has this model of supporting trusted users running trusted containers. Basically, if you can run, well, it's not exactly this way anymore, but essentially, by default, Docker tries to run the container as the root user, and so that creates all sort of headaches for people who worry about security way more than I do, and so that's kind of when Docker first came out, right? People in scientific computing and HPC space were really interested in using it because of all the advantages of containerization, but they really ran into these problems with like the security of Docker, and because on HPC systems, right, you have like this shared space, right? You can run, each of you can run, code on Expanse right now in, say, the shared queue. What that means is there's a bunch of different people on the same host node running different processes, right? And so, but if you're running in Docker in sort of the default way and everybody's running as root, then things can get a little out of hand, right? So if people start messing with other people's processes and things like that and files, and it's just not, it wasn't designed for this shared user environment. It was really designed for, there's like one team, they're running a database on a single node somewhere. It just makes it easy to deploy. Not with this sort of shared environment. We have hundreds of users, tens of users on the same node at the same time sometimes, right? and it also wasn't really designed for this sort of batch-based workflow that you've probably started using on Expanse with Slurm and submitting jobs and things like that. And again, for really high high-end HPC, doing tightly coupled, highly distributed parallel applications, it just was not designed for that. And well, maybe I'll have time to share an interesting story. We're working on that problem right now on a different system that is using Docker. So this is why Singularity was created, because people were really interested in the scientific computing and HPC space. They really were interested in using containers, but there was not a container sort of platform or engine that was made for the HPC space, right? And so this is how Singularity was invented. Excuse me, I'll drink water here. So Singularity was invented to bring all these advantages of containers, the reproducibility, portability, shareability, distributability of containers that Docker had. But it did two things different, right? It really wanted this no trust security model, so that when you run a container, you are your username, and you cannot do things to other users when you're running inside your container. And it really aimed to support HPC hardware like InfiniBand, GPUs, and sort of the scientific application space, because it came out of Lawrence Berkeley lab, right? So it's sort of a national lab doing high-end scientific computing, HPC. They needed a container platform. They just invented their own, so it's pretty cool. So these are the links to Singularity, and eventually they turned it into a company. This is the other link here for Scilabs, and I'll speak about that at the end. But there is a company that's trying to commercialize Singularity, and is actually adding a bunch of new features that are kind of more in the Docker space, but it's been more formalized basically since the project left Lawrence Berkeley, and they're I don't know how well they're doing, but I think we pay them a little bit for licensing, so they're doing okay at SDSC. So what are some of the features specific to Singularity that are kind of interesting and make it useful for the HPC space? So the first one, which is I think really nice, if you've ever worked with Docker, is the container image itself is a single file. Right. So if you've ever worked with Docker, Docker has this whole layering process of sort of a chain of files that go into building an image, right? And there's a lot of things that, there's advantages to that, but there's also it really hinders the reproducibility. And we'll go into a bunch of details, but you can imagine if, some layer along the chain gets accidentally updated without knowing essentially downstream, different applications and packages at different layers might change over time without you really realizing it. And so the environment you used to have might not be the same that you do have now when you rebuild your container. It's harder to maintain sort of this reproducible stability that you can in Singularity with this single image file. Now, again, to solve this security issue with Docker, right? They had this no trust security model. So basically, none of the processes run as the root user. The user cannot change their essentially user context. So basically, when you run the container, with Singularity, you're a certain user name on comment. If you look at the processes that are running in the container, they're also owned by your username on Expanse, right? So you can't change who you are inside the container from who you are inside the container, which you can definitely do in Docker. So this allowed it to support these sort of multi-tenant shared environments like our shared queue, essentially. And I'll talk a little bit more later about supporting the different types of hardware, InfiniBand, GPUs, and MPI applications.
Marty,
Yes.
before you continue, we have a question, and the question is: many genomics tools are in Docker format. Is there any solution to work around to the root escalation concern and still run it on university HPC?
Yes, I will actually show you. I think when we get to some of the more hands-on just examples, I'll show you. You can actually convert. So Singularity can convert Docker containers into Singularity. I think that's actually on my slide here. So maybe I'll just say that. On your question on InfiniBand, I'll talk about it a little bit. I can talk about it a little bit later, but essentially it's the high-speed network that we have on Expanse, and it's on many different types of low latency, high-speed, high bandwidth network that we have on Expanse between nodes. So if you're scaling out across many nodes, right, you need the network to be really responsive if you're doing sort of one of these highly coupled like ocean modeling or atmosphere modeling codes where you're trying to send data from the different boundaries as you broke up the problem between each other. So it's it's what our fancy network is on. It's not Ethernet, it's InfiniBand essentially is the network we use. So let me just answer the Docker question here in this slide. So well, starting from last, I guess, this is one of the most common use cases we see for Singularity, where there is, people who have developed Docker containers, but they can't run them on HPC system because we don't run Docker. Singularity allows you to convert a Docker container into a Singularity image, and then you can run it on, your university HPC system. In general, it works out of the box. There are a few like hiccups you can run into depending on how the Docker file and the original Docker container was built. There's a few quirks you can run into that can cause problems. And in those cases, what I have to do is usually rewrite the Docker file into the Singularity definition file to sort of rebuild the container. But in general, hopefully it's, the containers are pretty simple and, it'll just convert over and you can run it immediately. So that's definitely, that's one of the major applications that we see use cases for on our systems. The other two, the first was basically building and running applications that require like newer system libraries than are available on the host system. So, right, this is kind of coming back to this issue that I think I mentioned already, where we're running a certain operating system on Expanse, this CentOS 8.3. But a lot of applications, especially like really high profile ones like TensorFlow and PyTorch and this, AI machine learning space, those code bases are changing so fast and so constantly. They also usually require a newer operating system. They don't do a great job of like maintaining backwards compatibility. So this is one space where, I spend a lot of time helping people support those applications on Expanse and other systems. So we have to sort of use, and in those cases, both those applications usually assume you're using an Ubuntu operating system, which most HPC systems are not. And so we need that sort of ability to create that virtual software environment with a different operating system and all the things that we need inside those containers to run those newer applications on our systems, right? It's a real big process to update the operating system on an HPC system. We're working on that right now. It's a process, and it doesn't happen very often, right? It might happen every couple of years. But with these applications changing so fast, they're changing every month basically, with a new major release. So that's one of the other main things that we see. The other thing that we see is running commercial binaries, right? So you may have a commercial software license for whatever application that you might be using, maybe some sort of computer-aided modeling design, or what else do we see? Some sort of fluid dynamics code, that is put out by a commercial entity, but they don't ever release the source code, so you can't really build your own version of it. And so they have they've built it for you, but it might have very specific requirements that we can't meet on our systems, right? And so this is using a container to sort of wrap, as close to the environment that they're expecting for that binary. That's one way we can run those types of codes on our systems. So yeah, those are kind of the top three. Other than just having the container yourself to take it to any HPC system you want. This is kind of what we use them for when we're helping users a lot. And this is kind of the Singularity workflow, right? There's really 3 steps. It's like you have to, at some point, if you want to run your own container, you have to build your own container. You can convert, if there's an existing Docker container somewhere, you can convert that and build that image directly. But if you want to build your own custom container, the one limitation that I think is the stumbling block for most people is you really do need access to a system where you have root access. So like your personal computer, where you have Singularity installed. This is one limitation of the process, is to build an image, you still need root access. You cannot build Singularity containers on Expanse. You can download and convert a Docker container, but you can't like write your own custom definition file, which we'll talk about here in a second, basically this manifest of things you want to install, and build Singularity containers directly on Expanse. It's one limitation. I can maybe talk about some options you can try if you're interested in building containers. That's one of the main limitations. But once you do have your container, you can send it to any HPC system you want, and then you run your container on that system, right? So that's the first step is the hard step if you really want to get into Singularity and customizing things. And the way you would do that, if you're just working on your own laptop, you say have a Mac or a Windows machine, you're not running Linux natively on your laptop, then because you can install Singularity yourself if you're running your own Linux laptop. But if you're not, and you have Mac or Windows, the easiest thing I think is to use VirtualBox. If you've never used it, you can then run your own virtual machine on your Mac or Windows machine, install Singularity in that virtual machine, and you can build whatever you need there, right? So that's that's what I used to do a lot. I use other virtual machines now. So on the Exceed network, there's a system called Jetstream. So it's an OpenStack cluster. You can it's kind of like Exceed's own sort of Amazon Web Service, EC2 kind of thing. You just ask for a virtual machine. I go log in there, build things there, and that's what I do. One thing, if you are interested in doing this seriously, right, is when you're building Singularity images, just check what versions of Singularity that you will be running on, because you don't want to build your containers with the latest version of Singularity, because most HPC systems won't be running that version. So there could be some compatibility issues. And yeah. So my advice is usually, just use the same version on the HPC system you plan to run on. And if there's multiple ones, just use the lowest version, because it usually carries forward the compatibility, right? It's really, if you build with a newer version and take it to an older version of Singularity, is usually where you run into an issue. And yeah, let me stop here and see if there's anything in the chat. Can you run it on WSL? That's a good question, Salvador. Can you run it on the Windows system? So the Windows Linux subsystem, right? So if you're not familiar, Windows has this new Linux subsystem. I've never tried it. You can certainly try it. I would be surprised if it worked. Sorry. I always encourage Windows users to definitely try the Windows Linux subsystem though, because it's much easier for them to interact, I think, with if they're not familiar with the Linux environment, get some practice there. And it's also easier to interact with systems like Expanse and things, in a similar way. But yeah, I'm sure if you Google it, maybe someone's tried or asked that question. But I would be surprised if it works. But it's a good question. So let me stop here 1 second and just maybe point you to the Scilab's website, since we were talking about building containers. So if you're interested in building containers, you can try out the Scilab's website. They have Let's see if I can find it. Let's see. I haven't been here in a while. I don't know exactly where it is. They have a builder environment. So yeah, so they have this, they have their own cloud library. If you're familiar with Docker, it's like their Docker hub where you can store Singularity images and you can get a free account, and there is this remote builder. So you can actually, use Singularity, probably on Expanse even, to build a container by sending your Singularity definition file to this Scilab's remote builder. Let me just put this in the chat here. And you can write your own definition file, do it, and then it'll send it to cloud and then re-download it probably to Expanse. I haven't tried this. Maybe we can try this in the hands-on here. But that's one way you can get started if you don't want to go down the whole rabbit hole of setting up VirtualBox and things like that on your own Mac or Windows machine. This is maybe a simpler thing to try first. If you don't mind signing up for an account, giving them your information. I've used it in the past. The one limitation is I think you only get 10 gigabytes of storage. So it's really more of a trial account. You can build a few images and put them there and give it a shot. So that's one other option for trying to build your first container if you're interested. Okay, go back here to full screen. And when you're learning Singularity, if you go down, if you go on to want to learn how to do this from sort of end to end, there's really 3 main commands that you need to learn. The first is build, so you'll build your own container with the build command. But it's also, you can use the build command to convert, Docker containers and build from your scratch from your own definition files. So that's useful, and I'll probably show you an example for the Docker one when we switch over to just playing around with Singularity on Expanse. Shell is the next one. So this is kind of, if you needed to say effectively log into your container and poke around, this is kind of what this is useful for. It gives you this interactive access to the insides of the container and what's going on inside, right? And then the exec command is just, I want to run my container, exec run whatever command in my container is kind of just, it's basically like Singularity. Hey, this is the command I want to run, go. And so I have in these slides, you'll see I have some screenshots of examples in the past. I won't go into too much detail here. You can sort of scroll through and look at these as you want. Again, this is me building a Singularity file. So this SIF is the image, the Singularity image formats is what SIF stands for. This is the image that I'm trying to build from this definition file, which is basically so I think it's on the next slide, is this manifest of the things that you want installed inside the container. So it's basically, how should this image look from what you put here essentially. And again, the one limitation is you need root access to the system that you're building on, right? So that's unless you try the remote builder. But yeah, so if you want to develop your own custom Singularity container, this is what you have to do, right? So you have to write a definition file. So if you're familiar with Docker, this is like a Docker file. It's just the starting point for designing your own custom container. And there's different sections and things, and the documentation in Singularity is really good. You can go through and see the different sections that are needed to write to identify your container, set up the environment, and then start installing software. But it's really just the list of all the things that you want to be stored in that environment to create that container image that you're going to run, right? So I won't go into too much detail about like how to do that, but if you're interested, there's plenty of documentation on the Scilab's website, and I also do have a bunch of examples. So this is where I keep all of the containers that we use. So you can check this out and see what sort of the structure of what a definition file looks like for what I do usually. And there's a bunch of sections of containers that or of Singularity containers that I've never used. I just kind of, use the simplest ones, just basically, hey, this is what the container is, set up a few things, and then just install the software. That's kind of it. Right? But this is, the aim of this project is really just to share with other people, like, you can, hey, this is what our custom containers look like. And so it's easy place for you to start, and just want to make it available for people who want to build their own containers. Yeah. And yeah, these are just some screenshots of the build process here, finishing. It's actually a little bit out of date. This image here, it has a different format. I need to still update this for Expanse, or for the Expanse era. Basically, there used to be other different image formats for Singularity image. So this SMHI was slightly different than this SIF format. Again, the shell command is really useful for when you want to go into a container and poke around. So in these examples, when I was creating a bunch of just simple containers to just poke around and do things, if you look at this screenshot, what I do here is, I'm in my Linux terminal here. I have a few images that are built. There's my original definition file. And here I'm just looking at, like, this is which Python is available on my laptop itself here, right? And that's one version of Python 2.7.12, right? And then I have a version of Python 3 also here. But then I was like, okay, well, what kind of Python do I have in my Ubuntu Docker container, right? So if I download some default Docker container from Docker Hub, what Python do I have? So what you can do is you can download it, shell into that container, right? So it creates this interactive shell. Be like, okay, which Python? Oh, there doesn't seem to be a Python 2, right? There is only, oh no, there's not even a Python 3. So so in this case, right, I think in previous talks that I've given, we go ahead and modify this, because you can actually go in and interactively modify containers too with the build command. I'm not going to go through that here, but this is one thing why the shell command is useful. Especially when you're developing containers, you'll do this a lot, where you're like, oh, maybe something failed to get installed, so you have to log into the container and see, oh, did I get all the packages I was expecting, or did I not? So, and then this last third command that you really need to learn to use, which we'll definitely show you some examples today, is the exec command, right? So in this case, in this screenshot example, again, we have, I think I've modified some of these containers again. I've included Python now into this Ubuntu Docker image. And basically what I'm showing here is, again, the version of Python I have on my laptop, the version of Python 3 I have, and then I modified the Docker container to have Python 2 now. And so I said, okay, well, just run the Python/version command, but inside the container, right? And so you can see here, I run Singularity exec, the name of the container, and then the command that I want to run. In this case, just a simple check of what the Python version is. So you can see that the version of Python in the container is different than my version of Python 2 on the host system outside the container, right? That's the whole idea. I have modified this container, this environment, to my specific use case, and I have the version I want inside the container. And when you want to run a command, all you need to do is this format, Singularity exec, the name of the container, and then your commands that follow. Maybe I'll stop here and check the chat. Okay. Yeah, Maria. So the definition of the image, right? So there's really two ways to think about when people are talking about a container. Usually they're talking about either the container image, which is just the file that in Singularity is a single file that contains all of this software and data about the container environment, right? So it's the physical file that you point to and say, hey, you are my container, and I'm going to run some commands in you, right? And so on the flip side, when you run that, say, Singularity exec command, right, it takes that file, creates that software environment, and then runs the command in that running container process, right? So you have container images and container processes, right? So it's kind of, you think about a container image is a container at rest, a container process is a container in flight, right? So it's they're the same thing. I mean, people will use the term container interchangeably, right? And the image is really just that file that's sitting there that contains all the information you need to create that environment and run processes in it. Hopefully that answers your question. Okay, so let me just take a quick sip here. So again, some of the unique things about Singularity is it's supporting the HPC space. You could definitely have MPI-based Singularity containers. There's a few caveats of how this works, but I'll show you some examples. I think I have some examples maybe on Expanse. We'll see. But yeah, if your code uses MPI to do sort of distributed parallelization across nodes, you can do that not only natively as you might have done in the past, but you can also do that in a container. Again, there are some limitations. This is where one of these caveats comes in with if you're using MPI on an HPC system, you're usually 85–90% of the time probably using InfiniBand. And so there is this sort of requirement to make sure that there's not an easy way right now to get access to the InfiniBand drivers on the underlying host system in Singularity. You actually have to install the drivers yourself inside the container, and they have to be versions inside the container that are compatible with the ones that are outside the container on the underlying host system. So this is one caveat area that if you are doing MPI and Singularity containers on HPC systems, you just need to keep in mind. Again, if you are doing that and you're interested in that, definitely take a look at my repo, because I do this for our systems, right, where I have to sort of maintain the drivers inside the container that are compatible with the ones that we use on, say, Expanse. And it's not difficult to do. It's just something, it's one of these things that limits the portability sometimes, but it's easy to change if you have sort of a process in the definition file to just update the drivers when the system changes. So, and yeah, so I don't know if I still have this example, but this is one example we used to have of just, some electromagnetic propagation code that the reason we built it in a container was basically that it was so difficult to build anywhere else, right? So it's like there's just so many different specific dependencies, and it was just too hard to compile the code like natively on Comet at this time when we were running this example. And so this is one of those things where if you're doing research and you're using someone else's code and you can't get it to build easily, trying to do it in a container at least gives you that sort of unified environment that you have complete control over, where on some HPC systems you don't have complete control, right? Or no one has complete control. I don't have control. So this is one thing that we put in a container at one point, and it was, it worked out really well. I mean, we had actually a few different users that use it, surprisingly. I mean, it was kind of just a random code that one user asked for one time, and ended up having at least 3 or 4 people use this. So it paid for itself, I guess, over time. But so one of the things to point out in the container here, or in the screenshot here, is, again, this is just looking at a batch job file for this example job, right? And so again, it just looks like a normal batch job. You have your resource request to Slurm, define some environment variables, load some modules, and in this case, all I'm doing for an MPI job, which we haven't really talked about, I think it's probably in the next series, but the one thing that's different about running Singularity MPI jobs is what you have to do is also, in addition to the InfiniBand drivers, you also want you need compatible MPI inside the container and outside the container, because what you do when you run Singularity in a Singularity MPI job is you actually usually 99% of the time you'll run MPI. Well, if you're running multiple nodes, you run MPI outside the container. So you're using MPI from the host system itself, right? So that's why I'm loading these modules from the software environment that you'll see on Expanse or any HPC system, calling Singularity, pointing to the the image that I want to run, and then just running the commands that I need to run the application itself inside the container, right? And so by coupling this MPI outside the container, running this MPI application inside the container, as long as all the MPI bits are compatible in there, it'll run seamlessly like you would if there was no Singularity involved here. Right? See if there's a question here. Some distributed computing architecture with ledgers such as blockchain with Singularity. I don't have any thoughts on that topic right now. Maybe we can talk about that at the end. Sorry, Gary. Again, another popular area where we use containers a lot is with GPU computing. Again, I mentioned TensorFlow and PyTorch are pretty popular, and a lot of users are using those on our systems. And at least with, unlike the MPI InfiniBand issue above with the MEEP example, Singularity actually has a nice integration with GPUs now. Actually, all you have, again, you have a similar problem with the InfiniBand where your GPU drivers on the host system have to be compatible with either ones that you've installed inside the container, or in this case, Singularity actually will go outside the container, grab all of the libraries and driver information from outside the container and bring it in so it can use it on the inside, right? So as long as you compiled your code against, say, a compatible version of CUDA inside the container, you can, and as long as it's compatible with whatever that driver version and libraries are on the host system, all you have to do is throw this --NV switch, right? So it's kind of nice where it sort of does this automatic bind mounting I was talking about before, where if you really do need to use software outside the container, inside the container, this has sort of been a solved problem for GPUs in Singularity. And I think it even supports the newer AMD GPUs already and things like that. So again, this is just a screenshot example. I'll jump on Expanse here shortly. I think I'm almost done with the talk. Let me check the time. Yeah, okay, we're actually going pretty long. Okay. Again, so this is just looking at an example batch job script. You can come back to it later. The slides are already posted in the GitHub, so you can check it out there. I'll also show you where you can find some examples on Expanse if you want to play around with this. But yeah, it's again very simple. It's just you set up your batch job scripts. You load, in this case, load your Singularity module, because I'm just going to run on a single GPU in this example. You do Singularity exec. Now you add this flag, this --NV, to make sure you can access those NVIDIA drivers and libraries that are available on the GPU nodes. Point to your, in this case, TensorFlow image, run Python and the script that you want to run. It's really that simple. Once everything's set up, building TensorFlow containers is much more difficult. So don't try to do that yourself without talking to me, maybe. Yeah, so I mean, it's very easy to access GPUs in this case, right? So as long as everything's set up with the container correctly, or you just download one that's available, say, from Docker Hub, it should work pretty seamlessly. Yeah, so this is almost the end. So again, this is kind of just the high-level summary of what Singularity, what Singularity is and why it's kind of useful, right? It gives you this option to take your software and your software environment that you've customized to any HPC system that you're working on, right? And it's, again, with the caveats that have been mentioned about certain specialized hardware and networks and things like that. If you're just running something fairly straightforward on a single node, you don't need anything for the network, you don't need a GPU. Yeah, you could probably run your code anywhere as long as there isn't some issue with sort of the Linux kernel compatibility or something like that between the operating system and your container and the one outside. That's kind of the best case scenario where you could probably run for years with the same container, never change it if you're happy with that. Yeah, and so again, it's also if you're in the scientific and high performance computing space, this ability to maintain this sort of reproducibility over the lifetime of your project, your research project, your dissertation, maybe you're doing, it's a really nice way to think about these as little software units that you can sort of have a version of each one when you produced a certain set of results, so you can sort of track and maintain what the container definition file looked like here. You can always have a copy of that container that was built when it's that version of the definition file, and if you ever have to go back and reproduce something, you have this sort of workflow and just documented reproducible way to rerun your code from 2 years ago when you're trying to finish I don't know, some paper that's finally going to get published, or you get a question like how can you rerun this or something like that. Right? So it's a nice thing for the scientific computing community too. Okay, and now for one twist. If you are going to get into Singularity in any sort of serious way, there are complicating issues moving forward. There will be something called Aptainer coming to an HPC system near you. So just the backstory is, right, I told you that Singularity came out of Lawrence Berkeley Lab. That group who sort of invented it eventually went on to start a company and try to commercialize it. Well, sometimes those things don't work out so well. Or get complicated. The original founder of Singularity left the company, and there's been basically the projects. There was the commercial product from the company kept going forward. There was then an understanding when sort of this split happened. There was also a community supported open source version of it, right? The company does support continuing this open source version of the product. However, at some point they decided to the company decided to not follow the same repository of the open source project, so the projects started diverging. And so this is why Aptainer exists now. So Aptainer is the original sort of open source community project from this sort of split from the company. And it's just been accepted into the Linux Foundation. So it's not going anywhere. And a lot of HPC systems around the world run on Singularity, or run a lot of Singularity. And so I don't know exactly what's going to happen, but you will probably, if you work on HPC systems next year or two, you'll see Aptainer pop up if they don't have a Singularity license. So it's going to be basically the same thing, but the features will start to diverge at some point. And it's just something to be aware of if you're going to get involved in the space. We don't have Aptainer yet on our systems, but I know other people are already talking about it. So I think that's it. Oh yeah, additional resources here at the end. Check out the Singularity user guide. It's very well done, I think, if you really dig into it. Again, you have my example repos is available. We also held the first Singularity user group meeting at SDSC in 2019, so 3 years ago now almost. But there's a lot of cool videos and talks there. So if you're really interested in this stuff, I would definitely check that out. And then of course the Aptainer project is coming. They haven't released their first version yet, but it's supposed to happen in the next month, I think. So that is it for the talk. Now let me go to questions, and then for anybody who wants to hang around, I'll probably just drive and show you some examples of things you could do on Expanse, essentially. Let me just get my terminal here ready. Okay, so questions here. So Amin asks, is there some type of Singularity handbook or manual of any kind of command guide? Yeah, so that, again, I would go to, sorry, if you go to my slides, did I close it? Probably. So again, if you go to the end of the slides, just check out the Singularity user guide. It's really good. So you can check it out. Just gives you an introduction, quick start. That's where I would go for, if you're getting started and you want to like learn what the different commands are. Again, the top 3 that you really need to learn to really just work with it daily is build, shell, and exec. Yep. So next question. When it comes to transferring large singular file, what is your recommendation for transferring the files from our local computer to Expanse? So this is, this works for anything. It's not just for Singularity files, but if it's only a few gigs, you can just, SCP or SFTP it over. But if it gets bigger, there's something called Globus we have on Expanse. So you can use Globus. I don't know if we've talked about that yet in this series, but if you look at the Expanse user guide, I'm sure it says something about Globus. Yeah, data movement. So if you go to the data movement section, so we have a Globus endpoint. So if you don't know what that is, that's something you could go read about on the Exceed user portal too. So it's just for large data transfers between Exceed systems, that's what's recommended. So I won't go into too much detail there, but it's all available. But that's what you're looking for if you have a really big container. And then so Maria asks, are Singularity containers being replaced by apptainers, or will both exist? Yeah, I guess. Yeah. I don't know what's going to happen exactly. So my previous job from the one I'm currently in was working for one of the large Hadron Collider's computing teams, and we had like hundreds of sites around the world running Singularity. I'm betting they're going to move to Apptainer because they don't pay for software. So many people will move to Apptainer. Some systems will move to, we'll keep running with Singularity. Maybe like we have a license on Expanse for Singularity. You'll notice if I log into Singularity or if I log into Expanse, all right, and then module load Singularity. We actually have Singularity Pro. So it's one of the commercial license versions. So we get sort of, I don't think we have extra features, but we get extra support. Essentially, we have bug fixes and things like that that are important for running a HPC system. But yeah, it's all changed only in the last couple months. So we'll see how it goes. But yeah, I would imagine at some point, even us will probably have both on the system, because at some point, if there's a change to the image format, this CIF file format for the Singularity images or Apptainer images, those might diverge at some point, and then they won't be compatible. So it's going to be interesting support-wise, because then at some point also, we might have users come to Expanse and say, hey, I built this with Apptainer, but it won't run with Singularity. Yeah, it's just going to have something that everybody's going to have to work through in the space. Next question. Have you seen any comparison between performance of running HPC workloads natively versus using containers? Yes, you could definitely find, there's definitely talks out there and papers on this. And the short answer is there's almost never much difference. Like it's very hard to find significant deviation between native application performance and running out of a container. Interestingly, in some cases it runs faster in the container sometimes for different reasons, but basically, everything's sort of loaded into memory, and for some applications that helps a lot. Instead of sort of calling shared libraries off the file system, from a remote file system, it's actually kind of interesting. So yeah, you can actually get speed up by running in a container. people have seen. But yeah, in general, for most codes, you don't see a difference, I would say. Like, you really have to study it in detail to find the difference, and at most it's maybe 1% or 2 on the downside for some codes, maybe. But again, sometimes it's on the upside, a couple percent. So okay, so let me just move this stuff out of the way, and let's do some just quick examples of things you can try on Expanse. So let me just make a directory here, HPC CI training. Now, I think the first easiest thing to do would be, let me think. I have examples on Expanse. So if you're not familiar with where the examples are in Expanse, you can find them in CM shared apps, or is it examples SDSC? Yeah, examples. So I'll just put this in the chat. So if you're still new to writing batch job scripts and things like that, we have a bunch of different applications here where we have some existing example scripts. Let's see, which one do I want to use here? I think I'll probably just copy, and so you can just copy any of these example directories over to your home directory. And I think I'll just copy, I did PyTorch, or I did TensorFlow in the talk. Let me just maybe copy over the PyTorch example here, since that's kind of more popular in academia these days, I think. So you can, just copy that directory. I have a batch job script here. Yep. And so the only thing that you would have to change in here to run this code is the allocation project ID for the class, right? Now you can kind of see here, this is like a GPU example. It's going to run the GPU shared and the GPU shared partition. I'm just asking for 10 cores because that's how much we give basically for asking for one GPU, 30 minutes. And you'll see here, again, you need to load the Singularity module on Expanse. So, which is, if you're a previous user of Comets on SDSC, it wasn't that way, but you got to load this Singularity Pro module to get access to Singularity. And then here's the command, which is actually a little bit more advanced and complicated. So it might pique your interest of other things if you're going to go dig through the Singularity user guide, right? So I'm just running Singularity exec, right? With this other option, bind, which I'll come back to. I'm adding this --nv flag. Remember, this is to access the GPU drivers and libraries that are available on the host system. And then I'm just pointing to a container, right? And we have a bunch of existing containers in this directory here on Expanse. So these are the ones that we sort of build and maintain for users on the system, just because they're pretty common requests, and it's so like I said, some of these applications aren't easy for people to install themselves, and depending on what you do, or what version of PyTorch you want, and what you want to do with it, we do need these custom versions that we build ourselves. Maybe my next example is we'll actually maybe just pull a PyTorch container from Docker Hub maybe next, and run the exact same. You can run then we can run the exact same example with that container as well. But for various reasons, there's more advanced features in these codes that need to be built from source and things like that we do to support that kind of use, which the ones you'll find on Docker Hub they don't come with those features built out of the box. But yeah, so again, it's the same thing that we saw kind of in the example snapshots in the slides. Just run Singularity exec --nv, point to the container, call Python in this case, and the script that you want to run, right? In this case, this example, I think the script, you'll notice actually this script. I should just, yeah, it's kind of hard there. Not sure where to wrap it. This script is actually pointing to this /opt directory, right? So if I copy that and I do an ls on it, it doesn't exist, right? So where is that example code that I'm going to run? Well, it's inside the container, right? So I think I downloaded some example directory for PyTorch into the container. So if I do this makes it a little bit bigger. I think I have Singularity loaded, right? Yep. So if I do another command that we talked about, Singularity shell into the container, now I'm in the container and I can see, oh, there's the file. It's inside the container, right? So we've done our first Singularity command. You can Singularity shell into that container if you want to check out what's inside, right? So you can poke around into opt. You know, I have a few different things in here. You can see this is where I've installed a few things, right? So basically, if you look at my definition files, these are where all my opt is where I install all the sort of extra software outside of the operating system. So if you look at my PyTorch definition file, it's actually, I mean, I don't know. You pretty much have to use a Conda environment to build PyTorch from source for certain things. But so that's why I have a mini Conda distribution in here. Then I have my MPI version installed here, which looks like I definitely need to update this. This is old. I have a newer container already on Expanse. I think we just need to update the example. And then a directory for where I installed PyTorch, right? So this is this /opt, right? File system is inside the container, right? So we're shelled in, we're logged into the container here, right? Because if I go to outside the container and type /opt, it looks very different, right? This is from the host system. This is from the login node itself, right? So again, this is this thing about this file system isolation, right? Unless you specifically tell the container to see different pieces of the file system outside, you can't see them, right? It's just not part of the container. Let me go back here to the example script. And this point here about the file system isolation is a good one because you can see here, in addition to the --nv flag that I throw onto the exec command, I also have this --bind flag. And this is that flag that you throw to point to, hey, I want you to be able to see outside of the container in this spot, in this spot. And this generic setting here that I put points to the Expanse file system and the Scratch file system, right? So this Scratch file system, I don't know if we've talked about, but on every node, every compute node and GPU node on Expanse, there is a fast local hard drive that you can use to transfer data there, work on the data there, and while your code is running, because it's much more performant to put things there if you're doing a lot of heavy IO on that local hard drive than say working with your data over sort of the network file system, right? So it's going to be much slower if you work for it over there. So all this is saying is bind in that Scratch directory that I know is going to be available on those nodes. So if I want to say copy data over there, I can work with it. So this is kind of just a catch-all. The other one here is the /expanse file system. I don't know if we've talked about that. Maybe we talked about the Lester file systems and things last time. I forget. But I'll just show you a kind of an example here, right? So if we log back into this container, oops. So if I shell back into this container, right, I type /expanse Lester There's no such directory or file, right? So that's because I haven't bind mounted this external file system, which is available. Let's say Scratch and Kandes. Right, I have my own Scratch directory on the expanse list or file system, and if I wanted to get to that inside the container, I need to use this bind mounting process. That's what this other flag is for. So if I do just --bind / expanse, now I can see my project directory, right? So I poke that hole outside of the container so I can see all the stuff that's sitting on my Scratch directory on the expanse list or file system, right? So that's what this other flag was in this long sort of Singularity exec line. Now, let's see what. Let's see. This will definitely run. I'm sure. I think it's just an old example. So if you're interested, you could definitely run this example. I would recommend not running it too many times if you want to run it yourself, right? You don't have a lot of GPU time, I think, on the system. Let's see, let's go. So all you would have to do to run this example is, oh, I should run it there. Let me just cancel this real quick. I'm going to do this in the GPU debug partition, which should be faster. So it's already running. So here I can log into the GPU node, run SMI, and you can see I have already my container is running my Python scripts, and it's got, you know, some load on the GPU that I was assigned to. So this script is running. Again, it just looks like a standard Linux process. I can't tell necessarily that it's a Singularity container without more information. I think this NV host engine gives it away, but you know, it just kind of looks like a standard Python script that's running on a GPU. So we'll go outside the, log out of the node. Probably run. I don't think it takes that long to run. I forget exactly what the example. Oh, it's MNIST, so it should, you know, take like a minute or two. But again, if you're going to play around with this stuff, again, you might want to change over to just running it on the CPU nodes because you don't have a lot of GPU time. But you know, definitely feel free to, you know, give it a shot. You know, one of these examples. Let me just, while it runs here, I'll see if there's any questions. Yeah, that's why I was warning them, Nicole, not to run too much because it's a short job. So you only have, I think, 100 GPU hours. So this will probably run for a couple minutes and you'll get charged like for 1 hour, which is not great. But I should probably choose a different example next time. But yeah, so this is, I mean, but it was a nice example with the different bind mounting and then also the GPU NV flag. Now, what I'll do is, while we're waiting for this to run, the next thing we could try, which was asked, can we convert Docker containers to Singularity images? And that is definitely one of the use cases. So I'm just going to fire up Docker Hub. And let's just go grab like an official PyTorch image. Oh, come on. Where are you? All right. This is the problem. PyTorch project. Come on. This must be the official one, right? Yes. Now the question is, which one do we want? PyTorch, PyTorch. So we'll just get the latest one and see if it runs. So again, yeah, you can go to Docker Hub, find a Docker image that's available, and you know, hopefully run it. This one probably won't run on, yeah, it's probably not. Let's grab a one with at least CUDA so we can run it on the GPU again. Okay, let's see. Yeah, so you should be able to use the build command, but I think the one that has less problems these days, I think, is the Singularity pull command. So it's the one I use usually. I think the build command does the same thing under the hood, but they've changed a few things I'm not quite sure about, but we can try it. So if I do a Singularity build, I think it just calls the pull command. It used to, at least. So all I'm doing here is saying Singularity, try to build this Docker image by just taking the Docker string, pointing to the PyTorch repo and to the specific version of the container that I want. Let's see. Oh, yeah, sorry, I forgot. I need to give it an image name, obviously. So the equivalent command, which I think is actually what they use under the hood when doing this, is there is a Singularity pull command. So basically we do Singularity pull with the same thing, with the name of your image, and then pointing to the Docker image that you want to convert. Yeah, there's still some consistency things between commands that they can change in Singularity, but it's kind of historical. I think the pull command was before the build supported pulling it directly from Docker and building. So this is one way you can build a container on Expanse. It's not really what I would call building, it's just converting. Yeah, this is how you would do that for if you have an existing Docker image. Now, the question is, how long is this going to take? How did I close the Docker? To see how big it was. Might take some time. Oh, it's only 3 gigs. It shouldn't take too long. Question, can we choose an image with a downgrade CUDA version? Yeah, of course. Again, the thing that you might run into at some point is just compatibility, right, with the drivers, right? If NVIDIA drops support for some version of CUDA at a certain driver level, you'll sort of run out of room there. So yeah, I mean, you can for sure. Like we run, different versions of CUDA. I mean, across containers over time. It's just, again, at some point with the specialized hardware, you're sort of tied to what the vendors will support long term. So yeah, this is kind of what it looks like building an image from a Docker. Just sort of, again, remember I mentioned, if you're not familiar with Docker, I mentioned they have all these different layers. So what it's doing is downloading all these different layers and sort of reorganizing them into this single Singularity image file, right? Image format file. Okay, let me see. Oh, there it goes. Right when I open a new thing. Okay. So yeah, so that's just how you would convert a Docker container. Again, you could just, if you want to go in, poke around, see what's there, let's maybe at least confirm that it's a PyTorch image. Right? I assume it is, but you never know. Oh, interesting. So didn't we? All right. Yeah, no, we definitely, so that's kind of interesting, right? We definitely downloaded the Docker PyTorch 1.91 CUDA 11 CUDA 8 runtime image. But when we logged into the container and checked the version of PyTorch in Python, it says it's 110, not 191. This is why it's useful to know how to shell into the container. It's kind of funny. So yeah, so we download a new container. Let's see if our other job finished. The other job did finish. You can see the output file here. It's, again, if you've ever run some of these simple machine learning examples, the MNIST is kind of one of the classics. So there's your runtime. It's about 2 minutes. Let's see if it runs faster in the new container. I went from, we ran it in 1.5, like our custom build of PyTorch 1.5. Now maybe it'll run faster in 110. I don't know. Oh, I can't do this example. Darn. Maybe I can. So remember, in the example here, let me do this. My code is in the container, so I need to get it. Shoot. So one thing that's automatically bind mounted for you in Singularity is your home directory. That's why I was able to access that. So if I just copy from the container to my home directory, now I have a copy of the code. So let's see. All right, let's blow this other stuff away. I just want to use the new container. I don't know if this will work, but we'll see. So yeah, that's what the modified version is. I downloaded this container from, I want to run the new version of PyTorch, but with my same code. It's kind of all you would have to do. Just download the new container, adjust things as needed. In this case, I just needed a copy of my code. And if Nicole's still on, I keep wanting to type HLSMI. So there's my Python process again. It's running, right? And yep, now we can see that the GPU is loaded up. It seems about the same load as it was with the previous container. And so it should finish in maybe 2 minutes, maybe a little bit faster. But yeah, I think that's, unless anybody has any other examples that they want to see, that's kind of a nice, I think, overview of like, how to build a container from a Docker image, how to shell in a container, check things out, and actually submit a job to Expanse, and some of the flags you might need to use. Let's see who's still here. All right. Question. Yeah, yeah, Bart. The S was my image. Oh yeah, so the PyTorch image, the older PyTorch image has the .img format, and so that's actually yeah, it's an older container that we had from our previous system that we brought over, and so I think I mentioned briefly that the file formats for Singularity containers have changed over time. So the S image one is a slightly older version. So the CIF format is the new one. So if you build a container with a Singularity 3 version, a version of Singularity 3, SIF is the native format. I think you can probably still try to build old ones. I don't know. But obviously it still runs the old ones. So yeah, the SIF is just the newer format. Yeah, that's another good reason why we should update that example. But so let's take, oh, there it's done. Let's see if it ran any faster in the new container. I'm guessing not, but actually ran slower. So, you know, it's how things go sometimes. Probably need to update the example code. Anyway, that's kind of it for today. That's all I have. Unless some people want to stick around and ask other questions, I think we're done, and you could stop the recording